Hi, this is the first of two presentations concerning memory hierarchies. We will briefly recall what is a cache memory, and then we will discuss the operation of a direct mapped cache. Please notice that in this case I'll be following a previous book by the same authors entitled Computer Organization and Design. After watching this presentation and completing the learning task proposed at the end, you should be able to explain what is a cache memory and also how a direct mapped cache works. As you may already know, we can see caches as any intermediate storage between the processor and the main memory, created to speed up program execution by taking advantage of the principle of locality. Several cache levels may be used, and the memories used to implement them become slower and larger as we move farther away from the CPU. What you see on the left of this slide is an example of a small cache memory containing various data items that may have been recently used by the CPU. We see, however, that item xn had not been fetched from the main memory yet. So when the CPU wants to access it, we have a cache miss, and the execution of the program has to be delayed while the item is fetched from the main memory into the cache, as shown on the right here. So we may ask, how do we know that item xn should be stored in this specific memory cache position when we fetch it from the main memory? Well, here's one possible answer to that question in what is called a direct mapped cache organization. In this case, notice that the three least significant bits in the main memory address are used to define the address of the corresponding cache position. Of course, this means that various main memory positions may be transferred to and from the same cache position as shown here for the gray and blue items. So how do we know which of the corresponding main memory positions had its content transferred to the cache at any given moment? Well, the answer to that question is in the most significant bits of the main memory address, which are kept in the cache as a so-called tag, as we will see in a moment. So if the gray item currently stored in the cache has an associated tag of 01, then we know that it corresponds to the second gray item counting from the left in this main memory representation. Of course, we also need to say if the content of the cache is valid or not, since in the beginning it will be empty, and this creates the need for an additional bit associated with cache memory position called the valid bit. So let's consider an example to make sure that we understand how a direct mapped cache works. What you see here is a sequence of cache access cycles which generate 5 cache miss events and 4 cache hits. The two left columns show the corresponding addresses in the main memory, both in decimal and in binary form. And the rightmost column is simply an explanation why the cache memory address is derived from the 3 least significant bits in the corresponding main memory address. The following slides show what happens with the content of the cache memory as we move from top to bottom in this table. Notice that in the first access cycle on top here, the CPU reads from the cache to get the content of the main memory position with address 22. So let's see what happens. In the beginning, of course, the cache is empty, as shown in the left. So the first access cycle, as indicated here, leads to a cache miss event. The data item has then to be fetched from the main memory and brought into the cache, where it occupies the address defined by the 3 least significant bits in the main memory address. Likewise, the tag associated with that position takes up the value of the 2 most significant bits in that address. So after handling this cache miss, the content of the cache will be as shown in the right. Now the second access cycle again results in a miss, since the cache continues to be mostly empty. In this case, if you look again at the table shown in slide number 7, the CPU wants to read from the cache the data item that was originally stored in the main memory position with address 26 decimal. So the second data item has to be fetched from the main memory, stored in the cache, and the corresponding tag set to 11, as shown here on the left, according to the 2 most significant bits of the corresponding main memory address. Now the third access cycle, however, is a hit. If you look again at slide number 7, you will see that we want to access the content of the main memory position with address 22, but that has already been transferred into the cache. So, by the way, is this an example of temporal locality or spatial locality? Likewise, what follows is another hit, since the CPU wants to access the content of main memory with address 26, which is again present in the cache. The fifth cycle, however, is another miss, because the content of the main memory position with address 16 in decimal is not yet available in the cache. Make sure that you understand why the content of the cache will be as shown here after handling this miss event. Now, if you look again at the table shown in this slide number 7, you will see that the access cycle number 6 again leads to a miss, then a hit, then another miss, and finally another hit. And after handling these 2 last miss events, the content of the cache will be as shown here on the left. Please try to fill it in yourself and then compare your result with what you see in this slide. Well, to sum it up, may I suggest you to explain in your own words the operation of the direct mapped cache illustrated in this slide. How many main memory positions correspond to any single position in the cache in this case? And how many bits will be used to define the cache memory address? And how many bits will be used in the tag? Notice that you can find the answers to these questions in page 389 of the book. And that's it. Thanks for your attention.